Hello, my name is Nicolas Torres, and I am the project manager for the Arecibo Observatory Radiation Pattern Measuring Drone Project. I am joined by Jamil Gonzalez, Pedro Gonzalez, Carlos Fernandez, and Adrian Rivera, and we're going to talk about our progress this semester. The Arecibo Observatory is home to the second largest radio telescope on the planet, with a diameter of 305 meters on a spherical dish and low operating frequencies of 5 and 8 MHz. This is a unique structure capable of performing unique experiments. At the center of the dish, there are six dipole antennas that produce a circularly polarized directed magnetic field. This is also called the heating facility. Antenna characterization is a common test performed to observe how an antenna operates. Far-field measurements are performed in housed anechoic chambers to validate antenna operations. For the Arecibo Observatory, the distance to which we have to measure the far field is located 3 kilometers in the air. Because of the size and operating frequency, it is hard to obtain a measurement to validate its operation. When far-field measurements are not a viable option, we can resort to perform near-field measurements and used the fast Fourier transform to estimate the far-field pattern. From the equations below, we can obtain the far-field and near-field regions. As mentioned before, the far-field is located at 3 kilometers, while the near-field is the region below 400 meters for 5 MHz. Near-field measurements are performed using a grid pattern. With few equations, we can obtain a size and coordinates to sample an antenna according to the frequency and size. One reference states that the optimal near-field pattern is obtained at 3 lambda, meaning 180 meters from the antenna. Here, lambda is the wavelength for the frequency of interest. Now I will leave you with Jamil Gonzalez to explain our proposed solution to characterize the near field of the Arecibo Observatory.
Hi, my name is Emil Gonzalez, and I will be continuing the presentation. Our system,
On this detailed diagram of the antenna system, we can see how the signal will travel through the components. Once the microstrip Minder antenna receives the signal from the heating facility of Arecibo, this signal will go to the upper part of the diagram if it's a vertical polarization, or through the lower part of the diagram if it's a horizontal polarization. The first component that we'll encounter will be the balloon transformer that will unbalance the signal. Then it will pass through the matching circuit where it will be attenuated and will be matched the signal to eliminate any signal reflections. Then it will pass through the up converters to convert the signal into a higher frequency and finally go through the SDR to collect the data. The main purpose of the matching circuit is to obtain maximum power transfer to ensure the safety of the SDR and the components of the system from any reflection. It was decided to realize some tests to verify the impedance and the return loss of the components. The impedance expected was of 50 ohms, and the results of both polarizations and frequency was approximately 49.4 ohms. The return loss expected was of 50 dB, and the results obtained for both polarizations and frequency was approximately 43.7 dB. There are some margin of error, but we can conclude that the antenna components are serving their purpose. On this picture, we can see the physical appearance of the antenna system, where we can see the balloon transformer, the matching circuit, and the up converters. Now I pass you on with Carlos Fernandez to talk about the GPS.
As established, a GPS, which is a global positioning system, depends on a select number of satellites and can measure up to 5 theoretical meters horizontally in accuracy, even lesser when vertical. Meanwhile, a GNSS, which is a global navigation satellite system, provides and configures the information obtained by the GPS regarding geolocation and time. In the case of this project, a special type of GPS is implemented called RTK, which is real-time kinematic. It is capable of correcting data during tests and achieves precision in centimeters, therefore providing more accurate results when compared to regular GPS. In addition, it only requires a minimum of 4 satellites while operating, which is one less than that of a regular GPS. The objective of the GPS is to provide precise data on the location where a sample was taken. The RTK does this by using 2 stations, one to set its reference position, which is named base, and one that will be continually doing differential equations during the test, which is called rover. The RTK model used is the Precis BX305 manufactured by Tursus. This model had been chosen since it had 2 GPS frequency inputs that reduce connection error. In addition, we used the Tursus GNSS Center software for station configurations and data observation. The problem with our RTK model was its use of Bluetooth frequency. At 944 megahertz UHF, which is ultra high frequency, the communication was good for up to 200 meters. We need our system working past the 1.5 kilometer mark. It is for this reason that we are re-evaluating the GPS design and implementation.
This is the near field measurement data flow diagram. First of all, the drone is going to go to a specific location on the dish, where then the Python script is going to be reading data from the SDR. The SDR reads the IQ data from the dish and outputs it in binary. Therefore, the Python script is going to parse that data, where the first 32 bits are the real part of the value at the location, and the next 32 bits are the complex part of that number. And then it's going to create a binary file with those values of X and Y. And it's also going to create a text file with the GPS data for the current location. And it's going to do this several times. For later on, the MATLAB script can get those values at the same location and then average them. So after we do multiple runs at that certain location, it's going to go to another location. It's going to do it again for that location. So then after we gather all this data, it's going to be saved onto the onboard computer, and then with that data, it can be later retrieved for a MATLAB script to be able to calculate the average of each complex value of each location. And then with that average value of each location, it can get the magnitude and phase. And after it calculates all those values, it will save those values into a text file where it will contain a table of all the values needed. And this text file can then be used by another MATLAB script that can, for example, create a graph and to represent the near field table. To make sure that all of this is working properly, we can pass dummy data. We can generate binary data of X and Y values that we already know we already know the results of that after they're passed to the MATLAB script. But we want to make sure that the Python script is parsing that data correctly and storing it without modifications to make sure that when that data is read by the MATLAB script, that we get the exact same value we did originally. And that's it. Okay.
In the coming months and following into the next semester, we will perform the following tasks. We will research on the topic of undersampling. We will test the matching circuit, upconverters, the SDR, and laboratory with experimental data. We will finish this semester with a proposal for the redesigned GPS integration and test the SBC data collection software. Next semester, we will integrate the GPS system and obtain a measurement for the near field at the Arecibo Observatory. Finally, we will be writing a paper on our developed project for the scientific community. Thank you. For any questions, write an email to the following direction.